Okay, let's just jump right in. We are absolutely surrounded by plastics every single day, right? But have you ever really stopped to think about what they are? I mean, they have this whole secret life, this hidden molecular code that lets them be everything from a life-saving medical device to, the case protecting your phone. Today, we're going to crack that code.
I mean, seriously, think about it for a sec. How can the same basic stuff be soft and squishy in one form and then totally hard and rigid in another? One can stretch out and snap right back, while another would just shatter if you dropped it. It feels like it shouldn't be possible, but it totally is.
And the secret? Well, it's chemistry. Specifically, it's this amazing field called polymer chemistry. It's literally the science of designing and building giant molecules and tweaking their structure to create materials with the exact properties we want. And the key thing to get is that this incredible variety, it's not some happy accident. It is all by design.
So, let's start at the very beginning. How in the world do you go from some tiny, simple molecule to a solid material you can actually pick up and hold?
Well, it all comes down to this one essential process: polymerization. And honestly, the name kind of gives the whole game away. Mono means one, right? So monomers are the little single-unit molecules. Poly means many. So a polymer is just what you get when you link a whole bunch of those monomers together into one massive chain.
And this is the perfect way to picture it. Seriously, imagine a huge conga line at a party. Every single person is a monomer. When they link up and start moving, suddenly they're a polymer chain. It's that simple act of linking up that transforms these microscopic, individual molecules into these strong, tangible materials that we call plastics.
Okay, so how does this molecular conga line actually get started? Well, just like there's more than one way to cook an egg, chemists have all sorts of different recipes for getting these massive chains to form and grow. Now, the most popular recipe, the one responsible for a ton of the plastics you see every day, like polyethylene, polystyrene, PVC, it's called free radical polymerization. It's a really powerful and frankly super common way to make a huge range of materials. It basically works in 3 simple steps. First up, initiation. Think of this like lighting a match. An initiator molecule makes this super reactive particle called a free radical. Second, propagation. This hyperactive radical immediately grabs a monomer, which makes it reactive, and then it grabs another, and another, and another, and this incredibly fast chain reaction. And finally, termination. The party stops when 2 of these growing chains bump into each other and combine, and that's the end of the conga line.
But, that's not the only recipe in the chemist's cookbook. For more specialized jobs where you need absolute precision, chemists use different tricks. Ionic polymerization gives you incredible control. It's like building a chain link by specific link. And then there's coordination polymerization, which uses a special catalyst that's kind of like a guide, forcing all the monomers to line up in these perfect, orderly rows. That's how you get those super strong, high-density materials, like the stuff they use for industrial pipes.
All right, so now we know how the chains are made. But maybe the single most important thing that determines a plastic's personality is how those chains are all arranged. And this brings us to the great divide in the world of plastics. On one side, you have your thermoplastics, and on the other, you have your thermosetting plastics, or just thermosets. Pretty much every plastic you've ever touched falls into one of these 2 families, and believe me, they act in completely different ways. Okay, this is where it all clicks. So, on one side, thermoplastics. They're made of these long, individual chains that are all just tangled up, kind of like a bowl of spaghetti. They're held together by pretty weak forces. So, when you heat them up, the chains can slide past each other and the plastic melts. The key thing here is, this is reversible. That's why they're usually recyclable. Think of a plastic bottle. But thermosets, totally different story. Their chains are locked together permanently by strong chemical bonds, forming this rigid 3D web. When you heat them the first time, those bonds form and lock everything in place for good. They don't remelt, they just burn. And that's why, for the most part, you can't recycle them. All right, enough theory. Let's dive into some real-world examples and meet a few of these materials up close. Let's see how all this stuff actually plays out. First up, let's talk about a true legend, bakelite. This was actually one of the very first completely synthetic plastics ever invented, a revolutionary material made from phenol and formaldehyde. And its superpowers made it an absolute game changer. It's incredibly hard, it just shrugs off heat and chemicals, and it's a fantastic electrical insulator.
This unique combo is exactly why you still find it in things like panhandles, which obviously need to resist heat, and electrical switches, where you absolutely need that insulation.
So, quick pop quiz. Based on what we just learned, it's hard, it's rigid, and once it's molded, it is set for life. What do you think? Is Bakelite a thermoplastic or a thermoset? Yep, it is a classic thermoset. Once that phenol and formaldehyde cure, they form that rigid cross-linked network we were talking about. It is locked in place permanently. And that's what gives it that amazing heat resistance and stiffness. Okay, next up, let's meet a totally different kind of hero. This isn't a hard plastic at all, but a synthetic rubber, an elastomer, called Buna N.
So what makes Buna N a hero, especially in your garage? Well, it has this incredible resistance to oil, fuel, and all sorts of other nasty chemicals. Natural rubber would just swell up and disintegrate in those conditions. That is why Buna N is the absolute go-to material for anything that has to live in a greasy environment, like the fuel hoses in your car, the oil seals in an engine, or those heavy-duty protective gloves.
And for our last superpolymer, we have something really different. Meet silicone. See, it's not really built like other plastics. It's this weird inorganic-organic hybrid, and that gives it some truly unique abilities that other polymers just can't touch. The secret to silicone's power is that it kind of breaks the rules. Unlike almost all other plastics, it doesn't have a carbon backbone. Its chain is made of alternating silicone and oxygen atoms. This SiO-Si structure is incredibly stable, which gives silicones their amazing resistance to high temperatures. It's also flexible, it repels water, and it's chemically inert, which makes it perfect for literally everything from non-stick cookware and flexible bakeware to medical implants and waterproof sealants. So after that quick little tour, let's just zoom out for a second and think about the big takeaway from all of this. Look, if you remember one thing from all this, I want it to be this. Plastic isn't a single substance. It is a huge, diverse family of engineered materials. And whether it's the tangled, linear chains of a recyclable thermoplastic or the locked-in grid of a heat-proof thermoset, every single one is designed with a very specific molecular code for a very specific job. You know, we've gotten really good at making them strong, light, and durable. The really big question now is, what's next? What new molecular codes are scientists going to write to create the next generation of materials? I mean, are we talking self-healing plastics? Truly biodegradable ones? The chemistry is really just getting started, and the possibilities, they're pretty much endless.